Hello sir, this is Anva Gupta, 21 BDS 004, and I am presenting a comparison of four translation models that translate English sentence into Hindi. We'll be examining how well they perform in terms of accuracy and their blue score.
So these are the contents and we are exploring this model. So let's go to Helsinki model.
HNMT consists of three-layer LSTM network. This architecture is good in handling complex language structures like Hindi. So we have three layers. Layer 1, character level encoding. It reads word, but some words might be new. Break down words into their tiny in little letters or characters. By understanding these building blocks, the machine can figure out the meaning of the new word and translate it accurately. Now the second layer is token level layer. Token level bidirectional encoder layer is like a really smart translator who reads the entire sentence from beginning to end and then read it again in reverse order. This helps them understand the context and relationship between words and allowing them to translate the sentence accurately and smoothly. Now our third layer, characteristics token and BPE layer. It is like a lightning fast translator who can translate the entire sentence at once. They do this by focusing on the most important parts of the sentence by giving them weight. This allows them to translate quickly and accurately. We have used a huge database and of English and Hindi sentences from IIT Bombay for training as it is open source.
So let us see the code behind our model. So here we are installing transformer to get access the Helsinki transformer model, and we are saving our model path and dataset path, and we are training only 1% of our data for fast access. And here are the dataset, and now our processing all data and tokenizing it here. As you can see, my name is Sunna Gupta and I am from Ayodhya. Then here we in our data set and validate our data set. Here we compile our model and save the model in my drive only. So let's test our data. My name is Anva Gupta, it's my input, and output is coming as mera naam Anubhava hai. Here are some dummy list. As you can see, go to my GitHub repository, and from analytical library I have installed the blue score. My blue score is coming 5.1720.
Hello, sir. This is Rohit Saudhary, 21 BDS 011, and now we are going to move forward with neural machine translation. Neural machine translation is a type of machine translation that utilizes artificial neural networks to improve the translation of text from one language to another. We have recurrent neural network, that is RNN. RNNs maintain relation between words throughout the data point. RNNs maintain its relation between words by having access for each data point. The limitations of RNNs, that is, while RNN maintains some relation between the words through the data point, it cannot fulfill the long-term dependencies. This is because there is more weightage to the previous word than for the first words. And to limit the limitation, we have long short-term memory architecture. In this long short-term architecture, we have three primary gates. The forget gate decides the amount of information from the previous state that should be passed to the next state and what should be thrown away. The information from the previous hidden state h into t minus 1 and the information from current input xt is merged and passed to the sigmoid function. 0 decides whether it's thrown away and 1 decides whether we should take it. The input gate generally deals with the data to update the cell state. We merge and pass the previous hidden state h into t minus 1 and current input state, that is xt, into a sigmoid function. Then we multiply this sigmoid function with the tanh function, and the sigmoid output will decide which information is important to keep from the tanh output and into the cell state. The cell state contains information that we get from the output of the forget gate, which contains important information of previous state and the current information that we get from the input gate. The output gate controls the information flow to next hidden state by applying a sigmoid to previous hidden state and current input, weighing the new generated cell CT processed through tanh, effectively deciding what knowledge gets carried forward. Now let's look at our code. This is we are importing the files. As you can see, this is the data set. This is lines of English sentence, Hindi sentence, comparison of both English and Hindi sentences in a table. Here we are training the data. Here we can see x/train. We are saving the data by training the pickle file and testing the pickle file. And we have the encoder decoder architecture. This is the encoder architecture, encoder outputs, encoder inputs, decoder inputs and decoder outputs. We are compiling the modules and we are now training the samples. This is running the epochs. As you can see, the loss is getting reduced every time we go forward. The model save weights, we are saving the weights. The translation, the input English sentence here is verse by verse. Actually, in the translation is ek ek ayat. Predicted Hindi translation is ek ek ayat. So the model is pretty accurate. And now here we are looking at the blue scores. The average blue score is 23.
Hello sir, myself Mamidala Sriram 21BDS034. Today I'm here to discuss about transformers from scratch and how we have implemented. The transformer model was first introduced by Google. After that it has revolutionized the AI in the fields of LLMs. Now let us try to understand the transformers architecture and working of each component. Transformer architecture mainly contains of encoder and decoder structure. Before that, let us understand what is input embedding and positional encoding. The input embedding includes the process of tokenization where the sentence is divided into symbols, words or letters and they are mapped into vector spaces of size 512. later pass through positional encoding, where in positional encoding we want each word to carry some information about its position in the sentence. Later coming to encoder, the encoder mainly consists of multi-head attention and feed forward. It is like the brain of the operation. It allows the model to weigh importance different words in the sentence. Just like when we read certain words, we carry more weight. The attention mechanism allows the model to focus on these keywords, capturing long-range dependencies and understanding the context of the input. Once the model identified the important elements to attention, it processes them further. It's like fine-tuning the understanding gained through attention and making the model even more proficient in capturing nuances of the input. Now the decoder part. The decoder part also consists similar layers like the encoder, but has main difference in masked multi-head attention. Unlike the encoder's multi-head attention, the decoder's masked multi-head attention ensures that during the generation of each word of the output sequence, the model attends only to the words that have been previously generated. This prevents information leakage from future words and maintains the casual nature of the decoding process. Yes, sir. So as I've said, we have implemented our model from basic mathematical level. Let us see how it. So our model has many things like positional encoding, scale route products, sentence embedding, tokenization, as we have discussed, layer normalization, which normalizes our values, position-wise feed forward. Our encoding layer consisting all our components, which like multi-head attention layer normalization, and our decoder layer. You can refer to our code from the GitHub.
Greetings, sir. Myself Chintan Chawda, roll number 21 BDS013, and I am here to discuss about NLLB 200, No Language Left Behind by Meta. Generally, for translation models, ample amount of data in both the input and output languages are required for the proper training of a model. This means model requires to see pretty much every possible sentence to have good results. However, that's not the case with NLLB, which trains the model on all the 200 languages altogether. Meta created an initial model able to detect language automatically, namely language identification system. It then uses another language model based on transformers to find sentence pairs for all the scraped data. Using this, they make a unique database system which marks the completion of the database. It's taken from various sources like public media, then passed through Laser 3, and its output is checked by the expert. NLLB 200 model is transform based encoder decoder architecture like GPT-3. It takes a text sentence, encodes it in order to decode it. However, there are few modifications done to this model to scale up to more than 200 language. First one is allocating variable to identify source language of the input, and same is done with the decoder part to guide which language to translate to. This encoding technique encodes the sentence similarly no matter what their language is. Second major difference is that they use partially gated mixture of experts MOE model to achieve a more optimal trade-off between cross-lingual transfer and interference and improve performance for low resource languages. It is simply an extra step added in the transform architecture for both the encoder and the decoder part, replacing the feed-forward network sublayer with N feed-forward networks, each with input and output projections, and the transform model automatically learns which subnetwork to use for language during the translation. Coming to the coding part, first of all, we are installing the transformers, after which we are importing the pipeline dependency. The Facebook NLLB 200 model is being called using Hugging Face library. Coming to the next snippet, we can see that token has been generated, and after which it is passed through the model. In the next snippet, the translation model has been called, where the source language is English Latin and the target language is Hindi Devanagari. Coming to the next snippet, we can see that dataset has been imported, and we can see the predicted and the original Hindi translation. Finally, we install the NLTK library through which we can find this calculate the BLEU score.
Hello sir, my name is Mayank Kumar Shah, roll number 21BDS037. So I am here to explain the comparison between the previous model explained. So we will compare it with the help of BLEU score. So we will understand what is BLEU score. BLEU is stand for Bilingual Evaluation Under Study. Score is a metric used to evaluate the quality of machine translation output. Now, how it works? It works on n-gram matching, consecutive sequences of n words in the candidate translation with those in the reference translation. And second is precision. It measures the proportion of m-gram in the candidate translation. Brevity plenty. BLEU penalize the candidate translation that are unnecessarily short compared to the reference translation. Geometric mean. The precision score for the different n-gram are combined using the geometric mean to arrive the final BLEU score. Now, we will understand why we use BLEU, because simple and efficient, and its correlation with human judgment. BLEU score has been shown to have positive correlation with human judgment and widely used for metrics evaluation of machine translation system, making it easy to compare with different systems and track their process over time. Now we will see the result of all the algorithm we have used. So these are the outputs of our model.
We will see the result of all the model, and we have compared it with the BLEU score. Here we can see that Facebook NLB has 38.78 and Neural Machine Translation has 23.013 and Helsinki NMT has 35.1720. After all, we have compared all the model, and we can see that Facebook NLB has higher BLEU score as compared to other, that is 40% in Neural Machine Translation, Transformer 100%, Helsinki 9.31%. Thank you, sir.
These are our teammates: Anubhav, Rohit, Chintan, Ram, and myself, Mayank.